Good day everyone. Our topic is about the length. So here, I will discuss to you the length as a function. So we have here the function L, where the domain is script I. This is the collection of intervals in R. And then our codomain is the closed interval from 0 to positive infinity. Or this is equal to the set of positive real numbers union the set 0 and positive infinity. So this function here is defined as L of I, which is equal to the length of the interval. So for example, we have here the length of this interval from A to B. So it is just equal to B minus A, where A is less than B. Now what about if this is not an interval? Can we still get the length of this set if it's not an interval? So if A is not an interval, therefore the length of A is not defined. So it is not defined. Just like for example, if we have here the length of this set 1, 2, and 3 is not defined. It should be for the length, the domain should be the collection of intervals. Now our goal here is to extend the length function to the more general function. So that is, we have here the function where this is our domain and this is our codomain, such that the properties we have here, m restricted to I, is equal to the length of a function. So it means that the properties of the length function are being preserved. So let's have here our ideal properties of M. So we will look into a more general function which possesses all of these properties. So first, the domain of our function is the power set of R. It means it contains all the subsets of real numbers. Then we have here the codomain. So the same from the length function. So M is defined for all subsets of R. And then here, M of I is equal to the length of I for every interval I. So again, all the properties of the length function are being preserved. And if we have here the collection of pairwise disjoint subsets of R, now what do we mean by pairwise disjoint subsets? It means that every two subsets of R is disjoint. Every two subsets is disjoint. So if we take any two sets there, their intersection is empty. So that is the properties of our countable collections of sets. So if we are going to get this, that is M of the union or countable union of A sub I, countable union of the sets, it is equal to the summation of M of A sub I, which is equal, this is equal to M of A sub 1 plus M of A sub 2 plus M of A sub 3 and so on. So we call this as countably additive. It means M of the countable union is equal to the summation of M of A sub I. And fourth ideal property is, we call this as translate of E by Y. So we have here M of E, set E, plus Y where y is an element of the set E, is the same as M of E for all subset E of R. So, where here E plus Y is equal to this set. So, these are the ideal properties of a function that we are trying to look into. Now, we will try to see if there's such function that exists possessing all of these ideal properties. So let's have here the first definition for function. So a function mu, where the domain is sigma algebra script m to this from 0 to positive infinity. This is a measure if it satisfies the following. So mu, the measure of empty set, is 0. Next, this is countably additive. So I think this is the third ideal property. Okay, so we have here the disjoint collection of sets. Then we have this one. So take note, in this definition of the function, we call it as a measure, it satisfies the third ideal property. So this function does not possess all the ideal properties. Now let's have here an example. Let X be non-empty set, and this domain here is equal to the power set of X, because we know that power set of X is a sigma algebra. So we define the measure. We have your script m by 0 to positive infinity by mu of a, which is equal to positive infinity if a is infinite, if the set is infinite, and it is equal to the cardinality of a if a is finite. Now, is this a measure? Is this function a measure? So to show that one, we will try to show the two conditions here. So it should be that the measure of empty is 0 and countably additive. So based from the given definition here, of course, mu of empty set is, the cardinality of empty is 0. So the first condition is satisfied. Now, what about for the disjoint sets? If you take the union of disjoint sets, could be finite or infinite. So union of disjoint sets, of course, it is equal to the summation of the measure here. Summation of the measure, it means mu of a1 plus mu of a2 plus mu of a3 and so on is equal to mu of the union of a sub I. So you can try that one by using just finite sets. We can say that mu is a measure. Actually, this is called the counting measure. Now let's have another example here. We let X be a non-empty set, and still we have this one. This is a sigma algebra, which is equal to the power set of X. We will fix X sub 0 in the set X, and we define this function rather by mu of E, which is equal to 1 if x sub 0 is in E, and 0 if x sub 0 is not in E. So, it's very simple definition of a function. Now, to illustrate this function, let us consider this. Say we have here set x, and this is our set E. If x sub 0 is here in E, it means mu of E is 1. But if x sub 0 is outside E, or not in E, it means that mu of E is 0. That's it. We fixed x sub 0 be in x. Here, x sub 0 is still in x. Now, we will show that this function is a measure by showing the two conditions. First condition, it means that first condition is mu of mt is 0. So, is it 0? So, let's have here the first condition. We have mu of mt is equal to 0. Why? Since, of course, empty set has no element. So, x sub 0 is not in an empty set because it has no elements. Therefore, mu of mt is 0. Now, let us try to show the second condition. That is, we will show the countably additive. That is, mu of the union of a sub I, where I is from 1 to infinity, is equal to the summation of mu of a sub I, where I is from 1 to infinity, where a sub I intersection a sub j is empty for I not equal to j. So this is what we are going to show. Now to show this one, we will consider two cases. We have case 1, x sub 0 is in the union of a sub I. Then for case 2, we have x sub 0 is not an element of the union of a sub I. So, in this example, we want to show that this function is a measure. Now, recall that to show that a function is a measure, you want to show two conditions. First condition is to show that mu of mt is 0, and the second condition is to show the countably additive. So, we have shown already the first condition, that mu of mt is 0 in our previous video. So, the next condition is to show that mu of the union of a sub I is equal to the summation of mu of a sub I, where we have here pairwise disjoint sets. That is, a sub I intersection a sub j is empty, where I is not equal to j. So we will show two cases here. First case is when x sub 0 is in the countable union of a sub I. And then the second case is when x sub 0 is not in the countable union of a sub I. Why do we need to use two cases? Because we have here in our definition of the function, we have here when x sub 0 is in the set, so it is 1. When x sub 0 is not in the set, the mu of E is 0. So that's why we consider two cases here. So let's begin. So first case, when x sub 0 is in the union, countable union, it means from the definition of union, it means x sub 0 is in a sub I, of course for some I, and then since x sub 0 is in a sub I for some I, therefore x sub 0 is not in a sub j for all I not equal to j, since we have our condition that they are disjoint. Since they are disjoint, a sub I and a sub j, it follows that mu of the union of a sub k, where k is from 1 to infinity, is equal to 1 plus 0. Why? Because 1 when mu of a sub I. So mu of a sub I is 1 because we know that x sub 0 here is in a sub I for some I. And then we still have remaining summation of mu of a sub j, where I is not equal to j. So it means here, since x sub 0 is not in a sub j for all I not equal to j because they are disjoint, therefore from the definition of mu, each mu of a sub j is 0. So therefore the summation of this is 0, each a sub I, mu of a sub I is 0, summation of that is of course 0. Hence, we can write this one as summation of mu of a sub k, where k is from 1 to infinity if we add them together. So we have shown already that mu of the countable union of a sub k's is equal to the summation of the mu of a sub k's, where k is from 1 to infinity. Okay, we're done in the first case. Now let's proceed in our second case. We have here x sub 0. We let x sub 0 not an element of the countable union of a sub I. Then, by a remark, it states that if an element is not in the union, it means it is not in every set. So it is not in a sub I for all I. This means, by the definition of our function mu, if it is not in our set, then mu of a sub I is equal to 0 for all I. This means also that the mu of the union of a sub I, where I is from 1 to infinity, is also 0. Why? Because based in our assumption, x sub 0 is not in the union. So also mu of u sub I, the union of the countable union of a sub I is 0. Hence, we can write, hence we have mu of the union of a sub I, where I is from 1 to infinity, is equal to 0. which is equal to, if you're going to get the summation of this, 0 plus 0 plus 0 and so on, of course equal to 0. Where I is from 1 to infinity. So here, since mu of a sub I is equal to 0 for all I. So we're done showing the first and the second conditions. We can conclude now that mu is a measure. So that's it. And this measure here is called the Dirac's measure. Okay, let's have this proposition here. Let mu be a measure defined for all sets on a sigma algebra. First, if set A is contained in set B, where A and B are in the collection of sigma algebra of sets, then mu of A is less than or equal to mu of B. This is called the monotonicity property of mu. So as you can see here, A is contained in B, and of course the measure of A is smaller compared to the measure of B. Next here, we let here, this is the sequence of sets. Then, as you can see here, the mu of the measure of the countable union of E sub n is less than or equal to the summation of mu of E sub n. Note here that each set here, A sub n star, is in the collection sigma algebra, and the sets in the collection are not necessarily pairwise disjoint. And so we could have here less than, or it could be equal. So that's the end of our discussion for chapter 2. Thank you for listening.